This question is about the reactions of alkanes. Alkanes can be used as fuels. Give an equation for the combustion of heptane in an excess of oxygen. So because it says excess of oxygen, then we know that we're going to do complete combustion to give carbon dioxide and water. So if we look at the formula of heptane, C7H16, in oxygen, so O2, and we know that we're going to get carbon dioxide and water. So then we want to be balancing this equation. So we'll start with the carbons. There are 7 carbons in heptane, so we will make 7 carbon dioxides. And there are 16 hydrogens, so we will make 8 waters. Now if we add up the oxygens on the right hand side, we'll see that we've got 14 in the carbon dioxide and then another 8 in the water. So 14 add 8 is 22. So we want 22 oxygens on the left. Now in the formula O2, that means we would only need 11 O2s. Then it says heptane can be obtained from the catalytic cracking. So we need to remember about catalytic cracking. It's a high temperature, so high, slight pressure, zeolite, high, slight, zeolite. If you can remember that little rhyming, it'll help you remember catalytic cracking. And we're doing it of hexadecane at high temperature. Identify a suitable catalyst. The catalyst is the zeolite, high, slight, zeolite. Give one condition other than a high temperature, so that's our slight pressure. And give an equation for the catalytic cracking of 1 molecule of hexadecane to produce, we need to get 1 heptane, 1 cyclohexane, and then 1 other product. So we need to aim for 1 other product. So we're going to start with 1 hexadecane, which it gave us the formula of in the question. So we're just going to break that down, catalytic cracking. We know heptane because they also gave us that in the question. Now is our first bit of thinking, cyclohexane. So hex meaning 6, and a cyclic alkane has 2 N hydrogens. So we're going C6H12. And now we have to do some adding up to find our 1 other product. So we've got 7 carbons and 6 carbons, that's 13 carbons. We need another 3 to get to 16. We've got 16 and 12, that's 28 hydrogens, and we need another 6 to get to 34. Then it says alkanes can be used in the free radical substitution reactions to produce halogenoalkanes. Now we're being told specifically to make 2-chlorobutane from butane. Now because we're being given a specific product to make, we do need to show the location of radicals, and we're doing the propagation step. That's radical in, radical out. So radical plus molecule makes radical plus molecule. So we're going to start with our butane. CH3, CH2, CH2, CH3, and we're going to add our radical. We're trying to make chloro, so it's going to be a chlorine free radical. And that chlorine radical is going to grab a hydrogen to make HCl, and it's going to leave us with a radical, and we need that radical to be on carbon number 2. So we've removed the hydrogen from carbon number 2 and put the radical there. We take that radical forward to the next step, and we're going to react it with a molecule of our halogen to create the product we want, 2-chlorobutane, and regenerate the chlorine free radical to carry on reacting with more butane. So CFCs are groups of halogenoalkanes currently banned in many countries. They're used as solvents or refrigerants because of their effects. But they cannot be used anymore. They used to be used. So here we've got a CFC, and it says identify the radical produced from this CFC that is responsible for the depletion of ozone, and the radical that depletes ozone is chlorine. Explain with the aid of equations how it destroys ozone. So that chlorine radical is going to react with an ozone molecule and create a ClO radical and some oxygen. And then that ClO radical is going to react with some more ozone to regenerate our chlorine radical, but also break down that ozone and give us more oxygen. So we can see that the chlorine radical goes in, and then it is regenerated so it can continue to destroy more and more ozone.